Thank you very much. Hello, everyone. I'm Swagat from IUCA, and I'm going to talk about primordial black holes. First of all, thank you very much for giving me an opportunity to talk in this wonderful conference by ICTS. This talk is about formation of primordial black holes. We have heard about 3 to 4 talks on formation. And we have also heard a lot of talks on once primordial black holes are formed, what all implications they can have. But I'm going to address some issues on formation of primordial black holes, particularly in single field models of inflation. So I'm sticking to single field models of inflation, using a tiny bump as a local correction term to the base inflationary potential. This will become clear in a while. And I'm going to compare the kind of results that we get in these kind of models that I will talk. These are a set of models. This is not a particular model with, let's say, the near inflection point like potentials, which Rajiv gave a wonderful talk on, an extremely clear and wonderful talk, which makes my job a little easier. And I'm going to assume the standard, the primordial black holes, which are going to be formed in the radiation dominated epoch. So standard reheating history, short reheating, and then you go into the radiation dominated epoch. All right. So during inflation, you have seen this diagram that during inflation, your co-moving Hubble radius sort of falls, and then later it rises after universe starts to decelerate. You must have seen this in 2 to 3 talks that the CMB scales actually correspond to these large scale values. Okay, these things. The fluctuations, the modes which left the Hubble radius in the early times, they enter at late times and form the structure. And we have access to about 7 to 8 E-folds of early universe through CMB observations. But that's all. And for about 40 to 50 E-folds remain unexplored. And whatever happens in this small scale primordial universe during inflation could affect the early universe small scale physics. Okay, for example, if the fluctuations which are around 10 to the power minus 9 in power spectrum in the CMB could be higher at small scales, and if they are higher, for example, if they are as high as 10 to the power minus 2, then when they enter at early universe, they form primordial black holes. So this is the basic scenario. What I want to stress is that the earlier these modes enter, that means the later they left inflation, during inflation, the later they left the Hubble radius, the earlier they enter, the smaller is the black hole form. This curve, the audience have seen so many times that the inflationary fluctuations leave the Hubble scale at some early times, and they enter to form structure in the universe, and the CMB fluctuations only correspond to 7 to 8 E-folds. So we have a large part of the primordial physics during inflation unexplored. So primordial black holes can actually explore it. The important point is that the later these fluctuations leave, the earlier they enter, and the smaller the primordial black holes those are formed. So if you want to form higher, heavier black holes, then these fluctuations should leave closer to the CMB scale. And in inflection point like models, leaving closer to the CMB scale actually distort the CMB spectral index, which has been very well measured by now. And I want to propose a model where this problem doesn't happen. Okay, so that's the basic idea of my talk. So in the standard slow roll inflation, you have a asymptotically flat potential, and you have some part of the potential where the CMB fluctuations leave horizon, and then the potential sort of monotonically falls. When the potential monotonically falls, your slow roll parameters, which were small during CMB scale, they were percent level, they actually increase monotonically to become 1 where inflation ends. Okay, but in PBH formation, in the inflection point like features, what happens is there is a feature in between the CMB scale and the end of inflation, and this feature actually slows down the scalar field as it rolls. And so what happens as it slows down, the first slow roll parameter falls very sharply during this part. And if it falls enough, then the power can be amplified. But as the first slow roll parameter falls a lot, the second slow roll parameter sort of rises in its magnitude, and it becomes greater than 1 where the slow roll is violated. I want to mention, this has been mentioned, and this is usually sort of loosely called ultra slow roll phase. I want to mention that ultra slow roll means the modulus of eta is 3. In general, we should call it constant role, where eta becomes sort of a constant here. It could be 3, it could be a little less than 3. Okay. Then the scalar fluctuations you have seen, which satisfies a harmonic oscillator with a friction term. This friction term, this harmonic oscillator actually has a constant mode, and then there is a decaying mode because of the friction term. This friction term is increasing with time, okay, during inflation. As long as this is positive, you have a fall. So you have mostly a constant mode, which is the case when you solve it for your standard slow roll scenario. Okay. But during primordial black hole formation, since eta mod becomes greater than 1 and eta becomes negative, greater than -1 in that sense, amplitude wise, this term becomes positive. So exponentially decaying term actually becomes positive and grows exponentially. And since it grows exponentially, you have a growing mode for a transient period of time. It's a transient phase. This so-called ultra slow roll constant roll phase is actually a transient phase. And so you get power amplification. So this is the slow roll case. In the normal slow roll case, your power is highest around CMB scale in the observable scale, and it sort of decreases towards smaller scales. And it decreases only by 1 order over the entire 60 folds of inflation. But in the PBH feature case, near inflection point like potentials, the power is same at CMB scale, 10 to the power -9. Then it sort of rises at some intermediate scale. One has to solve it numerically because the slow roll is violated. And this rise in power spectrum actually gives rise to primordial black holes, as has been talked in many talks in this conference. I want to show something which has not been discussed in this conference. And particularly, I want to show why this power amplification actually happens. Okay. Now I have written the mode equation in terms of coordinate time instead of conformal time. And we see that this 2/3 eta h appears here. And there is a period, there is a transient period between which eta h modulus becomes greater than 3/2. Okay. If it becomes greater than 3/2, and it sort of remains constant, that's why we call it constant roll. During that period, whatever modes actually are leaving the Hubble scale get amplified. Okay. So think of this, look at this red curve, and these dots actually tell you at what time they leave the Hubble radius. So if they are leaving the Hubble radius at very early times, they get no amplification. It's sort of constant outside. This is your standard slow roll picture, mode freezing. But if you look at this yellow curve, which becomes super Hubble close to the time, from this period to this period is the time when eta is constant, then this gets an amplification overall. Similarly, this green curve, which actually leaves Hubble scale during the time when there is constant roll, this actually gets the highest amplification. Okay. And in between this constant mode to highest amplified mode, there is a mode, this blue mode, which actually gets a suppression, which has been noticed in many models. And it has been explained analytically also that you have a suppression in between. Okay. So now I want to compare between near inflection point models and the models that we proposed. Okay. So in near inflection point models, which work wonderfully to produce small mass, light mass primordial black holes, the PBH feature is sort of inbuilt into the potential. Okay. It's very difficult to separate the PBH feature and the CMB scale, even though one can mathematically usually talks of asymptotic regions where CMB is, but it really doesn't satisfy. It actually affects here. For example, if you want to produce a little higher primordial black hole, you want to push this feature a little towards the right, then the potential corresponds to the CMB part actually falls a bit. This causes a tilt, a higher tilt in the scalar power spectrum. Okay, so it is not possible to produce higher mass primordial black holes. You can produce 10 to the power minus 14 solar mass black holes very well. In most of the models, it's very difficult to produce 10 to the power minus 12 solar mass black holes, which have these black holes have induced gravitational waves, which come in the LISA band, and then it is almost impossible to form planet mass and solar mass black holes in these models without distorting the CMB spectral index. So our proposed model has the form of a local feature, which is a tiny bump, which doesn't affect the overall asymptotically flat potential. So the CMB part is not affected by it, and you have a local feature. And this feature could be closer to the CMB scale without affecting this. This actually helps you to produce even 100 solar mass black holes without distorting CMB parts, CMB NS. Okay, and the PBH scale and the CMB scale are very well separated in this model, as you will see in a while. So the proposed model has a simple mathematical form. You have a potential which is composed of a base inflationary potential. This base potential is any asymptotic.
Sorry, Swagat, since we are running. Sorry, Swagat.
Yeah.
Since we're running late, could you please finish within 2 minutes? I mean,
sure. Yeah.
That would be good. Okay,
yeah.
That's
fair. Thank you. So this base inflationary potential could be any potential which is asymptotically flat. And then you have 1 plus a correction term. And this correction term is local. And this correction term has a height, which I call A, which is small compared to 1. This is actually in percent level. And it has a width sigma, which is small compared to the Planck scale. Okay? And you could actually try any base potential which satisfies CMB observation, any asymptotically flat potential as the base potential. And you could try any local tiny bump. For example, I have given you a Gaussian bump and a hyperbolic bump, but you could try any. It works for all of them. Here, in the next 2 slides, where I had demonstrated that how these things work. This is for KKLT inflation and Gaussian bump. So you get the height of the potential very low, and the width is also low. Okay, and it's such a small distortion to the potential that I have zoomed in here. It's a tiny bump, really. Okay, since I have to speed up, I'll finish here. I'll just show you that that the power is amplified very well, and you get abundant amount of primordial black holes without any trouble. The same thing also happens for alpha attractor model. It's a different model. Same framework, it's just that you change your base potential and change your bump, Gaussian bump. Okay, what works for a bump also works for a dip. So our correction is both positive and negative. Okay, so it works for a bump. It also works for a dip. So there is a symmetry between bump and dip, and you get exactly same amplification. And so there is a symmetry. And our model also satisfies this maximum growth bound, which is set by these authors last year. So this also satisfies this maximum growth bound. And it can produce planet mass black holes because it can also produce solar mass black holes. So there is no trouble. Okay, so I will summarize that a tiny local bump or a dip can actually amplify power enough to form primordial black holes. Since it's a local feature, it doesn't affect the CMB spectral index. This is very important. And it can produce heavy solar mass black holes of the order of hundreds of solar mass to very light solar mass black holes with equal ease. And it has a simple functional form where the PBH feature is just tiny correction to already generic base inflationary potential. If you're interested in our work, you should read this paper. Thank you very much for your attention.
Thank you very much, Swagat, for finishing in time.